Imagine waking up on Mars. The room is silent. There are no birds outside, no wind moving through trees, no smell of rain, no distant traffic, just the quiet mechanical hum of a machine keeping you alive. You take a breath. Oxygen enters your lungs. For a moment, nothing feels unusual. Then you remember something. Every molecule of oxygen inside that room has been manufactured, recycled, monitored, or deliberately stored. Because outside those walls, there is almost nothing you can breathe. Mars has an atmosphere, but for a human being, it is effectively a vacuum. The air is mostly carbon dioxide. The atmospheric pressure is less than 1% of Earth's sea level pressure. There is almost no breathable oxygen. So, on a permanent Mars base, oxygen would not simply be something we consume. It would become one of the most carefully managed resources in the entire settlement. Every breath would have a history, and every breath would eventually need to be recovered. Because on Mars, the question would not be, how do we bring enough oxygen? The real question would be much more unsettling. How do we build a civilization that never runs out? To understand the problem, imagine the first settlers arriving. Their spacecraft lands on the Martian surface. Cargo is unloaded. Habitat modules are connected. Power systems come online. Water tanks are secured. Food is stored. Oxygen reserves are checked. At first, everything seems manageable. The settlement might arrive with oxygen tanks and other consumables from Earth. But this only works for a temporary outpost. A permanent civilization is different. Imagine hundreds of people living on Mars. Then thousands. Every person needs oxygen continuously. A resting adult consumes roughly hundreds of liters of oxygen each day, depending on activity and environment. Multiply that by an entire settlement and the numbers become enormous. You could ship oxygen from Earth, but launching every kilogram of consumable material across interplanetary space would be extraordinarily expensive, and eventually the settlement would face the same fundamental problem as any isolated spacecraft. It must close the loop. Oxygen has to be produced locally. Water has to be recovered. Carbon dioxide has to be removed. Waste has to be processed. And almost nothing can simply be thrown away. The first major source of oxygen would likely be something that already surrounds Mars, its atmosphere, carbon dioxide. To us, carbon dioxide is useless for breathing, but chemically it is an enormous resource. Each molecule contains oxygen. The challenge is extracting it. One approach is electrolysis. Instead of splitting water, a system can use an electrochemical process to separate oxygen from carbon dioxide. NASA has already demonstrated this basic concept on Mars. The Mars Oxygen In Situ Resource Utilization Experiment, known as MOXIE, operated aboard the Perseverance rover and successfully produced oxygen from Martian atmospheric carbon dioxide. It was a small demonstration, but its importance was enormous. For the first time, humanity had manufactured oxygen from another planet's atmosphere. The machine was not creating oxygen from nothing. It was taking something Mars had in abundance and turning it into something humans desperately need. Imagine that technology scaled up. Instead of a small instrument inside a rover, imagine an industrial facility operating continuously outside a settlement. Mars air enters the system. Carbon dioxide is processed. Oxygen emerges. The oxygen is compressed and stored. The remaining gases are released or processed further. Suddenly, the atmosphere that once made Mars deadly becomes part of the life support infrastructure. The planet itself becomes a raw material warehouse. But there is a problem: energy. Every oxygen molecule extracted from carbon dioxide requires energy, and a permanent settlement would need enormous amounts of it. That means Mars would not only need oxygen factories, It would need power factories. Solar arrays could provide electricity. But Mars is farther from the sun than Earth. Dust storms can reduce sunlight. Dust can accumulate on solar panels, and during certain periods, sunlight becomes less reliable. A settlement depending entirely on solar power would therefore need massive energy storage systems, or alternative generation. Nuclear power becomes extremely attractive. A compact reactor could provide continuous energy through dust storms, night, and seasonal changes, and that energy could keep the oxygen systems running. Because on Mars, an oxygen plant that stops for too long is not merely an industrial inconvenience. It becomes a countdown. Every habitat would therefore need redundancy. Multiple oxygen generators, multiple storage systems, multiple power sources, multiple emergency reserves, because eventually something will fail. A valve will break. A pump will stop. A filter will become contaminated. A software system will crash. A power cable will fail. And when the nearest repair crew is millions of kilometers away, there is no replacement truck coming tomorrow morning. This is where the architecture of a Mars base becomes almost frightening. The settlement would need to behave like a living organism. Air would constantly circulate. Sensors would constantly measure its composition. Machines would constantly remove carbon dioxide. Humidity would be controlled. Trace contaminants would be filtered. Oxygen concentration would be monitored. Pressure would be monitored. Leaks would be detected. And somewhere in the background, another system would be quietly producing new oxygen. Every room would effectively be connected to a planetary-scale artificial lung. But producing oxygen is only half of the problem. The other half is keeping it, because oxygen is incredibly valuable. If a habitat develops a leak, the settlement is literally losing atmosphere. And unlike a leaking building on Earth, you cannot simply open a window. Mars is outside. The pressure difference between the habitat and the Martian environment is enormous. A small puncture could become a serious emergency. The settlement would therefore need multiple layers of protection. Individual rooms could be isolated. Airlocks could separate sections. Pressure sensors could identify abnormal changes. Automatic doors could close within seconds. Emergency oxygen masks could deploy. And reserve oxygen tanks could provide enough breathable atmosphere for occupants to survive while the damaged section is repaired. The habitat itself might even be divided into independent pressure zones. Instead of having one enormous volume of air, the settlement could contain dozens or hundreds of smaller compartments. If one section fails, the rest remains alive. This is the same principle used in spacecraft and submarines. On Mars, it becomes a matter of survival, but there is another source of oxygen that may become even more important. Water. Mars contains water ice. Some of it is buried beneath the surface. Some exists as frozen deposits, and if future explorers can reliably extract and purify that water, they gain something incredibly valuable. Not just drinking water, not just agricultural water, but oxygen. Water is made from hydrogen and oxygen. Through electrolysis, electricity can split water molecules into hydrogen and oxygen. The oxygen can be used for breathing. The hydrogen can potentially be stored or combined with carbon dioxide to produce other useful chemicals and fuels. Suddenly, water becomes the foundation of an entire industrial cycle. A Mars base could extract ice from the ground, process it, purify it, send some into life support systems, send some into agriculture, send some into electrolysis, recover oxygen, store it, and recycle the water again. The settlement would slowly become less dependent on Earth. But there is an even more elegant possibility. The oxygen you breathe today could become the oxygen someone else breathes tomorrow. Consider what happens when a human exhales. You do not breathe pure oxygen in and breathe pure oxygen out. Your body consumes oxygen and produces carbon dioxide. That carbon dioxide cannot simply accumulate. Too much becomes dangerous. So the life support system captures it. It may remove the carbon dioxide directly from the habitat atmosphere. Then the captured carbon can be processed. Some systems could use carbon dioxide as a feedstock for chemical production. Others could potentially recover oxygen through different processes. The goal is not necessarily to create a perfectly closed ecosystem. That is extraordinarily difficult. The goal is to make the system as closed as practical. Waste becomes feedstock. Carbon dioxide becomes raw material. Water becomes recycled infrastructure. And oxygen becomes part of a continuous loop. The ideal Mars settlement would waste almost nothing, because every kilogram discarded is potentially something that had to be imported from Earth. And every kilogram imported from Earth represents energy, launch capacity, transportation, and time. Eventually, the settlement could begin producing not only oxygen, but the machinery needed to produce oxygen. That would be the true turning point. At first, Mars would be dependent on Earth. Earth provides machines. Earth provides spare parts. Earth provides food. Earth provides oxygen reserves. Earth provides everything. But as industry develops, Mars begins manufacturing components locally. Metal, glass, ceramics, plastics, pipes, pressure vessels, solar equipment, replacement parts, and eventually, perhaps, components for life support systems themselves. The settlement begins to close its industrial loops. This is when a Mars base stops being a research station and starts becoming a civilization. But the most dangerous part may not be oxygen production. It may be human error. Imagine a technician entering an oxygen processing facility. A sensor reports abnormal pressure. Another sensor says everything is normal. The system begins switching automatically between redundant machines. A warning appears, then disappears. Nobody notices. 3 hours later, atmospheric oxygen levels inside one habitat section begin falling. At first, the change is almost imperceptible. Then people become tired. Headaches appear. Reaction times slow. The alarms finally activate. Doors seal. Emergency oxygen begins flowing. The settlement has entered survival mode. On Earth, an accident like this might trigger an evacuation. On Mars, evacuation means entering an environment where you cannot breathe. There is nowhere else to go. That is why a long-term Mars settlement cannot depend on a single oxygen factory. It must be designed around failure. Every critical system needs backups, and every backup needs another backup. Some oxygen would be stored as a strategic reserve, perhaps enough to support the settlement through major equipment failures. The settlement might even maintain underground emergency habitats containing independent life support systems. If the primary base becomes uninhabitable, people retreat underground. The doors close, the outside world disappears, and the artificial atmosphere continues circulating. This is what makes Mars so different from Earth. On Earth, the environment is part of the life support system. On Mars, the habitat itself becomes the environment. The walls become the atmosphere. The machines become the weather. The oxygen generators become the forests. The recycling systems become the rivers. And electricity becomes the invisible force holding everything together. A Mars civilization would essentially build a tiny artificial Earth inside a hostile planet. But eventually, perhaps, something even stranger could happen. The settlement could begin producing oxygen faster than its inhabitants consume it. Not because oxygen is abundant, but because the settlement has become industrially mature. Large atmospheric processing facilities operate continuously. Water extraction systems feed electrolysis plants. Agricultural systems contribute oxygen through photosynthesis. Carbon dioxide is continuously captured, Oxygen is stored underground in enormous reserves. The settlement begins building its own atmospheric infrastructure. At that point, oxygen stops being a consumable. It becomes an engineered resource. And perhaps, centuries from now, the descendants of the first settlers could look back at the early missions with disbelief. They would hear stories about astronauts arriving with tanks of compressed oxygen. They would see photographs of tiny habitats surrounded by endless red desert. They would remember that every breath once depended on equipment shipped from another planet. But their world would be different. Their oxygen might come from underground factories, from processed Martian water, from enormous atmospheric plants, from forests growing beneath artificial sunlight. Perhaps one day from engineered ecosystems designed specifically for Martian conditions. Yet even then, Mars would remain unforgiving, because the planet does not care how advanced the settlement becomes. Outside the walls, the pressure remains dangerously low. The atmosphere remains mostly carbon dioxide. Radiation continues to pass through the thin atmosphere. Temperatures remain extreme. Dust continues to move across the surface. And if the machines stop, the planet begins reclaiming the habitat almost immediately. That is the uncomfortable truth behind building a permanent civilization on Mars. We would not simply be colonizing another world. We would be constructing a machine large enough to keep humans alive. A machine made of habitats, reactors, oxygen generators, water processors, farms, sensors, airlocks, pipelines, batteries, computers, and thousands of interconnected systems. And every one of them would depend on the others. Power produces oxygen. Oxygen keeps people alive. People maintain the machines. Machines extract water. Water produces oxygen. Agriculture produces food. Humans produce carbon dioxide. Life support systems remove it. Waste is processed. Resources return to the cycle. The entire settlement becomes one enormous artificial ecosystem, a fragile technological organism living on a dead planet. And perhaps the most haunting thought is this: the first permanent inhabitants of Mars may never hear the wind the way we hear it on Earth. They may never breathe an atmosphere they did not engineer. They may never walk outside without a pressure suit. They may never experience the simple luxury of opening a window. For them, oxygen will not be invisible. It will be monitored, measured, stored, recycled, protected, and every time they breathe, they will be participating in a system that humanity built from scratch. One failure could threaten a room. A larger failure could threaten a habitat. A catastrophic failure could threaten an entire settlement. But if humanity learns how to maintain that invisible cycle for decades, then something extraordinary happens. Mars stops being merely a place where humans survive. It becomes a place where humans can stay. And perhaps that is how another world begins. Not with a flag, not with a city, not with a giant spacecraft landing beneath a spectacular Martian sunset. It begins with something far smaller, a machine quietly extracting oxygen from carbon dioxide, a pipe carrying water beneath the ground, a sensor watching atmospheric pressure, a reactor humming in the darkness, and somewhere inside a sealed habitat, a human being takes a breath. The machine records it. The oxygen level drops by a fraction. The system responds. More oxygen enters the room. The cycle continues. Outside, Mars remains silent, cold, empty, and almost completely hostile to life. But behind a few centimeters of engineered material, humanity has created something the planet never intended to contain. A breathable world,